A team of astronomers was not looking for anything unusual. They were simply cross-referencing star data from a space telescope with older archives, running what should have been a routine comparison when something in the numbers stopped them cold. Buried inside one of the oldest, most tightly packed clusters of stars in our galaxy, a narrow band of stars that should have existed simply was not there. Not fewer stars than expected, not dimmer stars than expected. An actual gap, a missing slice carved directly out of the population of an ancient stellar family, sitting in data captured just weeks ago by Europe's Euclid space telescope, a detail that took researchers completely by surprise. Nobody planned to find it. Nobody predicted it. And right now, nobody can fully explain why it exists. This is the story of what Euclid just captured, images and data so strange that astronomers are still scrambling to understand exactly what they are looking at. To understand why this discovery matters, you first need to understand what Euclid actually is and why it was built in the first place. Launched by the European Space Agency in July of 2023 from Cape Canaveral, Florida, Euclid is not designed like most of the space telescopes people are familiar with. It was not built primarily to zoom in on single spectacular objects the way Hubble or the James Webb Space Telescope often do. Instead, Euclid was built to do something far more ambitious in scope, mapping the shapes, positions, and distances of literally billions of galaxies across roughly a third of the entire night sky, all in the pursuit of understanding two of the deepest mysteries in modern physics, dark matter and dark energy, the invisible forces that together make up about 95% of everything that exists in the universe, despite the fact that nobody has ever directly detected either one. Dark energy is the mysterious force believed to be responsible for the accelerating expansion of the universe, for reasons scientists still do not fully understand. Dark matter is an invisible form of matter that does not emit, reflect, or absorb any light, making it undetectable directly, yet its gravitational influence on how galaxies rotate and bend light is unmistakable. Euclid's mission is built around indirectly mapping these two invisible forces, and in the process of that enormous survey work, it has already started stumbling onto discoveries nobody expected to find, waiting for exactly the kind of high-resolution imaging Euclid was built to provide. That NGC 6397 gap is a perfect example of exactly this kind of accidental discovery, and it is worth sitting with for a moment before moving on to the rest of what Euclid has found. NGC 6397 is what astronomers call a globular cluster, an incredibly dense, ancient collection of hundreds of thousands of stars, all bound tightly together by gravity, orbiting as a single unit. It sits relatively close to Earth in cosmic terms, making it one of the most studied globular clusters in the sky, and for decades, astronomers assumed they understood its basic structure fairly well. Then, in June of 2026, scientists working with Euclid's newly captured data noticed something that should not have been possible according to standard models of stellar evolution. Instead of a smooth, gradually shifting distribution of stellar brightness across the cluster's population of red dwarf stars, the small, cool, incredibly common stars that make up the bulk of most star clusters, there was a distinct, narrow gap, a specific brightness range where stars simply did not appear at all, almost as if something had reached in and surgically removed an entire slice of the population. What makes this discovery particularly striking is that the team was not even searching for anomalies of this kind when they found it. Researchers were originally focused on studying stellar motion and the overall structural dynamics of the cluster, cross-referencing Euclid's fresh observations against archival data from the Hubble Space Telescope and the European Gaia mission, when the unexpected pattern in the data emerged almost by accident. Scientists have since described the discovery as serendipitous, a word astronomers often use when careful. Painstaking survey work stumbles onto something nobody was specifically looking for, precisely the kind of unplanned breakthrough that large-scale sky surveys are uniquely good at producing. Earlier, much fainter hints of similar brightness gaps had been spotted in isolated star fields elsewhere in the galaxy, but Euclid's deep, high-resolution imaging of this particular cluster provided by far the clearest, most undeniable evidence yet that this strange gap is a real, measurable feature, not simply a statistical fluke or a limitation of older, lower-resolution instruments. So what could actually cause a gap like this to exist inside an ancient star cluster? Astronomers currently have several competing theories, none of them fully confirmed, which is exactly what makes this such a genuinely open scientific mystery, rather than a settled explanation waiting to be summarized. One leading possibility involves a poorly understood transition point in how red dwarf stars generate and transport energy internally, a shift in stellar physics that could theoretically cause certain stars to skip rapidly through a specific brightness range rather than lingering there the way models currently predict, effectively creating a temporary void in the population at any given snapshot in time. Another possibility involves the incredibly crowded, gravitationally violent environment inside a dense globular cluster itself, where close stellar encounters and gravitational interactions between neighboring stars happen far more frequently than in more sparsely populated regions of the galaxy, potentially disrupting or altering the evolution of certain stars in ways astronomers have not yet fully modeled. Neither explanation is confirmed. Both remain active areas of ongoing research, and until more data comes in, either from Euclid continuing its survey or from follow-up observations using other instruments, the true cause of this brightness gap remains, quite literally, unexplained. Before we go any further into just how many strange discoveries Euclid has already produced in its short time operating, if the idea of a space telescope stumbling onto genuine cosmic mysteries, almost by accident, is the kind of story that fascinates you, go ahead and hit like and subscribe right now so you catch the next one. The NGC 6397 gap is far from the only strange thing Euclid has captured recently. Earlier this year, in February of 2026, an entirely different and in some ways even stranger discovery emerged from a collaboration between Euclid, the Hubble Space Telescope, and the ground-based Subaru telescope in Hawaii. Astronomers identified what they are calling a dark galaxy, a galaxy that appears to be almost entirely composed of invisible dark matter, with only the faintest, sparsest smattering of visible stars scattered across it. The discovery began when Hubble's high-resolution imaging revealed a tight, unusual grouping of 4 separate globular clusters, sitting inside the Perseus Galaxy cluster, roughly 300 million light-years from Earth. Isolated globular clusters typically orbit within a host galaxy, bound to it by that galaxy's gravity. So finding 4 of them clustered together tightly, with no obvious bright galaxy nearby to host them, immediately struck researchers as unusual. Follow-up observations combining Euclid, Hubble, and Subaru data then revealed something that had never been directly observed in quite this way before: a faint, diffuse glow of extremely dim starlight surrounding those 4 globular clusters, providing the first direct evidence of an underlying galaxy so overwhelmingly dominated by dark matter that its own visible stars barely register at all. Researchers involved describe this as the first galaxy ever detected, specifically because of its globular cluster population, rather than being detected the traditional way, through direct observation of its stars or gas. In other words, astronomers essentially found a nearly invisible galaxy hiding in plain sight, identifiable only because of a small, unusual clue: 4 star clusters sitting suspiciously close together with almost nothing binding them but an otherwise undetectable, overwhelming amount of dark matter. That discovery matters enormously for cosmology, because finding more of these nearly invisible dark matter-dominated galaxies could help. Scientists finally start piecing together exactly how dark matter behaves in clusters on smaller cosmic scales, something current models still struggle to accurately predict. Then there's the Einstein ring, arguably the most visually stunning example of Euclid stumbling onto something extraordinary almost by pure chance. Back in September of 2023, just months after Euclid launched, engineers were still in the middle of routine testing, checking that all of the telescope's instruments were functioning correctly before beginning full scientific operations. During that testing phase, Euclid sent back a batch of images that were deliberately left slightly out of focus, simply meant to confirm basic instrument functionality rather than produce usable science data. But while reviewing one of those blurry test images, Euclid archive scientist Bruno Altieri noticed something unusual: a faint hint of a specific, extremely rare gravitational phenomenon hiding inside the fuzzy image. Follow-up observations confirmed exactly what he suspected. Euclid had accidentally captured an Einstein ring, a nearly perfect circle of light formed when the gravity of a foreground galaxy bends and warps the light of a more distant background galaxy directly behind it, creating a glowing halo effect first predicted mathematically by Albert Einstein's theory of general relativity over a century ago. What made this particular discovery so remarkable was not just the phenomenon itself, since astronomers have identified other Einstein rings before, but exactly where it was found. The galaxy responsible for the lensing effect, called NGC 6505, sits a relatively modest 500 million light-years from Earth, making it essentially a next-door neighbor in cosmic terms. Astronomers had been studying this particular galaxy since the 1880s, more than a century of observation, and not one of those earlier studies had ever detected the ring of light surrounding its center. It took Euclid's exceptional resolving power to finally reveal something that had apparently been sitting there, hidden in plain sight, the entire time. Researchers involved in the discovery noted that finding gravitational lenses this close to Earth is particularly valuable scientifically, because nearby lenses allow astronomers to test the predictions of general relativity with far greater precision than lenses located billions of light-years away, essentially providing a natural, cosmic-scale laboratory sitting right in our own galactic backyard. These kinds of accidental discoveries are not simply happy coincidences either. They are, in a very real sense, exactly what Euclid was designed to enable, even if the specific findings themselves were never predicted in advance. Euclid's core scientific strategy depends on capturing extraordinarily wide, extraordinarily detailed images covering enormous patches of sky, then relying on both artificial intelligence systems and citizen science volunteers to comb through that flood of data looking for exactly these kinds of subtle, easy-to-miss anomalies. By the time Euclid completes its planned 6-year survey, scientists expect the telescope to have identified somewhere in the range of 100,000 strong gravitational lenses scattered across the sky, roughly 100 times more than astronomers had cataloged from all previous surveys combined throughout the entire history of modern astronomy. Each one of those lenses represents another potential opportunity to stumble onto something as strange and unexpected as the NGC 6397 brightness gap, or the nearly invisible dark galaxy hiding among 4 clustered globular clusters in Perseus. In June of 2026, Euclid also delivered something slightly different from these scattered individual anomalies, an enormous, breathtaking mosaic image of the Milky Way's own crowded galactic center, assembled from 26 cumulative hours of deep space observation across 9 separate telescope pointings. The resulting image captured roughly 60 million individual stars in a single unprecedented view, described by scientists involved as the largest, most detailed photograph ever taken of our galaxy's center in visible light. Buried within that massive image, astronomers also identified specific, smaller features worth studying individually, including a glowing red emission nebula, roughly 26,000 light-years from Earth, formed by clouds of gas being actively energized by newly forming stars nearby. That single image is expected to help astronomers hunt for hidden exoplanets throughout the crowded galactic bulge, using a detection technique called microlensing, which relies on precisely tracking tiny, temporary brightness changes caused when a foreground object's gravity briefly magnifies the light of a background star, sometimes revealing the presence of an otherwise completely invisible planet orbiting somewhere in between. What ties all of these discoveries together, the mysterious brightness gap inside an ancient star cluster, a nearly invisible galaxy dominated almost entirely by dark matter, a century-old galaxy suddenly revealed to be hiding a gravitational lens nobody had ever noticed before, is a simple but genuinely exciting truth about where Euclid's mission currently stands. This telescope has barely gotten started. Euclid has so far surveyed only a small fraction of its total planned coverage area, with its first major cosmology data release still scheduled for later this year, incorporating a dramatically larger survey footprint and multiple additional passes over its deepest observation fields. If genuinely strange, currently unexplained phenomena like these are already surfacing from just a fraction of Euclid's total planned observations, it raises an obvious and exciting question about exactly what else might still be waiting inside the enormous volume of data this telescope has yet to fully capture and analyze. Scientists involved with the mission have also emphasized that many of these findings will require significant additional follow-up work before researchers can move from describing an anomaly to actually explaining it with confidence. The NGC 6397 brightness gap will likely need dedicated spectroscopic observations before astronomers can determine which of the competing theoretical explanations actually accounts for the missing stars. Similarly, the dark galaxy in Perseus will require deeper observations to precisely measure how much dark matter it contains relative to its visible stellar population. Genuine scientific mysteries rarely resolve themselves quickly, and Euclid's team has been notably careful to present these findings as open questions, actively under investigation, rather than settled explanations already fully understood. If uncovering exactly what strange, unexplained phenomena a space telescope keeps stumbling onto almost by accident is the kind of story you find genuinely fascinating, make sure you are subscribed and have hit like on this video, because Euclid's mission has barely even started, and there are almost certainly far stranger discoveries still waiting inside the data this telescope has yet to fully analyze. None of what Euclid has captured so far involves anything supernatural, anything artificial, or anything beyond the reach of established physics. Every single one of these findings represents a genuine, unresolved gap in scientific understanding, exactly the kind of mystery careful, patient observation is designed to eventually solve. Astronomers do not yet have all the answers, and that is precisely the point. Somewhere in the billions of galaxies Euclid still has left to survey, there's a very good chance the next genuinely unexplained discovery is already sitting there, quietly waiting to be noticed.